right, so could you introduce yourself and then just talk about the project that you guys have been working on for the past year?
Yeah, my name is Carolyn Christie. My team is Team 11, and we've been working on the autonomous throwing arm. So this next slide here. So the overview of the project is that we were building an arm that can throw to a target and use feedback technology in order to hit the target more accurately. This project is interdisciplinary because it's got feedback design, image processing, there's a mechanical design of the arm, and computational modeling as well for the trajectory of the ball. So in the corner, I have just a basic diagram of what the project looks like, the setup. So the arm is in the left, and then the dotted line represents the ball, and the catcher would be on the right. So moving on, this project has a ton of applications all over the world. The military has like an exoskeleton, and this could be applicable to that because the way the motors work, it represents a limb. Or a school did a project where they created an arm for a kid who had lost his arm in an accident, and it could actually help him live a normal life. So our mentor is Dr. Armando Rodriguez, and he's working on building a robotic circus with several of his graduate students. So we had a great source of knowledge to ask for help for various places where we got stuck or ideas for the project. So our throwing arm design, we chose a mechanical design that was fairly simple. It only has 2 degrees of freedom. Because that way, since we are electrical engineering students, we can focus more on the control system of the project and the image processing. So on the right side is a picture that I took after we finished printing our arm. So on the left here, I have a plot that we made for the trajectory with various different drag coefficients and linear drag and quadratic drag on the ball for the air friction. And then at the top, that's the form of our controller that controls the motors in order to have the ball hit the target accurately. And on the right, this is just kind of a little sketch. So we planned to create like a grid against a wall and throw the ball while recording it. So that way, it's almost like a GPS system. We can figure out the, given the angle that we threw it at, where the trajectory actually is, to compare that to our simulated model and make sure everything really matches up. So our image processing, we actually had to have 2 different methods because we needed to track the target, which is supposed to move up and down in order to catch the ball. And we need to know the X, Y, and Z coordinates of that. That target's not always going to be in motion, so that's a requirement for the image processing. The ball is going to be moving very quickly, so we needed a different method for that. So for the target, we used a color mask method, and there's a little video in the corner that kind of shows how it works. And so that worked really well for the target because it just bases off the color of the target, and anything moving around doesn't interfere with its tracking. And then here we have a bit more advanced code. This is our final code. And in the color, that's the depth feed from our Connect camera. So that way we can see how far back it is, and that tells us what parameters we need to throw at. And then this was the image processing for the ball, and you can kind of see a little video of the ball launching across the screen. So it's able to track it really fast, and that's what we need. So we can tell where the ball landed so that our controller can adjust and get it to throw in order to actually hit the target.
All right, cool. So after going through all of this, what do you think was the hardest part of your project?
So we actually had an issue. The motors that we picked for the arm, it doesn't work quite fast enough. So our prototype does not launch the ball yet, so we weren't able to actually integrate the image processing with ARM yet. But we actually are all very interested in it and are planning on working on it over the summer to actually make it work so that our mentor can use it in his robotic circus.
Awesome. And what do you think you learned the most out of this project? Was it like something software based? Was it something hardware based? Or was it just like soft skills?
The method of research, definitely, because none of us have had much experience with that. Image processing, none of us had seen that, and now we've seen a whole lot more than most electrical engineers ever have. And coding on Arduino, that was something new to us as well.
Okay. Awesome. Well, thank you for taking the time to share your project with us, and good luck to you out there for Demo Day.
Thank you.
Yep.
Wait, one moment.
All right, so introduce yourself, and then you can tell us about the project that you've been working on for the past semester.
Yeah,
Past
so
2 semesters.
my name's Jaron Fox, and we're Team 18, and we've been working on the solar-powered self-driving car project.
Okay, and then you had a little demonstration about how it works, or
Yeah.
I guess you could explain first in theory how it works, and then show us.
So I mean, like, we're using an Arduino Uno. That's like, it's what talks to all the components. So it's talking to, it has 3 sensors here to detect like collision around it. And then we have obviously some solar panels on top. And it has 2 modes. It has charge mode and it has drive mode. So when it's in charge mode, it's just charging the batteries. And in drive mode, obviously just driving around, avoiding collisions. And it's self-driving. I'm not using a remote or anything to control it. So yeah, that's basically how it works.
All right. Do you want to give us the demonstration of it?
Yeah, let's do a demo.
All right. Cool. All right. So what do you think the application of this in the real world would be, and kind of compare your product to stuff that's already maybe out there?
Yeah, I mean, obviously Tesla comes to mind with their self-driving cars, having a sensor knowing what's around them, avoiding collisions and whatnot on the road. And then on top of that, you know, if it's integrated with solar technology to power the battery on board, it's going to be a lot more like economical for consumers, cheap, and like way better selling point. And then we just have all this free energy from the sun that we're, for the most part, not utilizing. So I think, you know, I think those two technologies together are like a perfect match.
Yeah. So after you've been through all this and, you know, you have your final end product, what do you think was the most difficult part of this project?
I'd say the most difficult part was trying to get it to drive straight.
Okay.
It wasn't really one of the biggest facets or biggest key points of the project, but we implemented a gyroscope and got the coding working for it. We had the right motors turn faster than the left motors if it was going off a bit, just to adjust it.
Yeah.
But it would still drive kind of crooked, so we just kind of threw away that idea. We didn't really need it.
Okay.
So it all worked out pretty good in the end.
Okay. And what do you think you learned the most from this experience? Was it something like technical, or was it something more like soft skills? What do you think?
I mean, I would definitely say a lot of both. I don't have too much experience with like constructing like technical objects. So that was a really fun part about it. And I would say the coding part, you know, getting all the code to work together so it didn't really like overload the Arduino Uno that we're using. So trying to make really concise code was also like one of the biggest things I learned. And how easy it is to charge batteries with solar panels. I mean, it's super simple. You connect positive to positive, negative to negative, and you can charge them really easily.
Nice.
So,
So if you had a little bit more time or, you know, more money,
yeah.
what do you think is something you could add to this project to make it better or more efficient or something like that?
Yeah, so if I had more money, I would replace these sensors with laser type radar sensors so that they're way more accurate and so that they could kind of have edge detection, so they could see like past an edge to know like we don't want to go that route and we want to go a different direction, just to add more of a like wide functionality to collision, you know.
Okay.
And I would say, you know, tweaking it more to get the car to drive straighter.
Yeah.
So.
That'd always be nice.
Yeah.
All right. Well, thank you for your time and thanks for the cool demo that you showed.
Yeah.
And good luck out there for the rest of demo day.
Yeah, you're welcome. Thanks, Richard.
Thanks.
All right. If you could just help us put those
Yeah.
back on that shelf.
Sure thing.
So could you introduce yourself and then talk about the project that you've been working on?
Yeah, for sure. So my name's Amanda Smith, and I'm working on a team actually of biomedical engineering majors. I'm the electrical engineering on the project, and we're basically working on an intraoperative scoliosis load sensor that basically would be used to basically quantify load within the surgery, because right now there's a problem with the surgeon's not really having a way of quantifying that load, and so they're basically going off of experience of, as that they're screwing in these screws into this person's back to correct their back. They don't really have a way of saying, like, okay, you've placed enough load onto this person's back. So basically our device would be used, implemented on the glove of the surgeon, and it would be measuring the gripping force that the surgeon is placing on the tools to indirectly tell them, okay, you've placed enough force onto this onto the system. So my portion of the project specifically is about kind of quantifying or seeing what the gold standard of what this device should function as. So basically looking at taking off-the-shelf components and being able to measure the pound force and show that from front to back end that this device would work.
Awesome. So you have a video of the device working or
Yes.
testing? All right. Yeah, so you could play it and kind of explain what's going on in the video.
Okay, perfect. So I'll just play it right now. Okay, so basically what's going on is that I'm about to press down on the load cell that's underneath that bar, and we're going to see values. The value of on the voltmeter actually change. So the signal is actually coming up. That's the raw signal coming from the load cell. So that basically shows that I'm putting about 26 pounds of force. I know that kind of gets a little blurry right there because I'm trying to press a lot of force onto it. It's actually really difficult, more difficult than I thought it was going to be to place pound force onto the load cell. But basically, so this kind of shows the front end of I'm placing force onto the load cell, and then after that, unfortunately, I'm not a very good videographer, so I couldn't get what the sensor shows or what the Bluetooth shows. But basically, next this is the pop-up screen. I know that it's in thermometer format. It turned out that Bluetooth is a lot more complicated than I initially thought. But you can see that as I increase the force on the load cell, the value on the Bluetooth also changed. So I know it says degree C, but that's actually the pound force value that I'm changing and placing onto the load cell. So there you can go, you can see that's where I was pressing really, really hard, and now I'm coming kind of back down, and so you can see it kind of fluctuate between the same kind of values that I was placing on the load cell in the last portion of the video.
Okay, awesome. So now that you've worked through this project, what do you think was the most difficult part of this project for you?
I would say that the most difficult probably was the differential amplifier. So initially, I'm using a PSOC 6.2 microcontroller, and I thought that I was going to be able to use the internal amplifiers that were within the device, but it turns out that they actually have a operating voltage of nothing below about 0.3 volts, but the signal that you get onto the load cell is on a millivolt range. So it literally could not recognize that there was any kind of signal being placed onto the onto the GPIO pins on the microcontroller. So I had to go through and actually design a differential amplifier, which wasn't originally part of what I thought I was going to have to do, and to amplify the signal before sending it into the microcontroller. So that was a little challenging in the way of I've only ever dealt with ideal amplifiers in class. Yeah, and so actually having to go through and design an amplifier was kind of a new experience with the kind of more hands-on side of it. So I know how an amplifier functions from classes, but actually going through and figuring out, okay, this is the kind of feedback loop I have to have on it. These are the different resistor values. All that kind of stuff was a little bit more challenging than I thought it was going to be initially.
So what do you think what's the one thing you'll take away from this experience, like the thing you've learned the most about?
I would say the thing that I learned the most about was to always start on the analog first. I kind of started on the analog second. I decided to play around with the PSOC and do more information, or do kind of more with the PSOC and trying to get all the voltages coming out of the analog to digital converter working and all these different kind of like more the digital side, and I spent a lot more time on that, and then decided to go to the analog and actually connecting the load cell to the microcontroller, because at first I was just doing, and most of the semester was spent using just a voltmeter and changing the voltage on the voltmeter to make sure that the analog to digital converter was working, the Bluetooth and everything. Right. And then I transitioned over to the analog side of it, and I realized that I probably would have been able to get a little bit better result if I would have started with the analog, started with the operational amplifier, and getting a good signal out of the load cell before moving over to the digital side of it.
Cool. Well, thank you for sharing your project with us and explaining how it works. And good luck out there for the rest of the demo day.
Thank you.
All right. So could you introduce yourself and then talk about the project that you've been working on?
Sure. So my name's Hunter Riley. I'm a member of Team 2 along with Guillermo Salcido, Marco Martinez, and Skylar Hart. And our project was to collect and characterize radio frequency signals of interest using a software-defined radio. The main application of this project is for the military intelligence field, but specifically signal intelligence, and it is a replacement for expensive ASIC technology, or is it what's the acronym for that? Application-specific integrated circuits or boards like that. So it replaces what could fill up a whole room full of hardware with just a computer and a radio front end. For our project, we kind of broke it down into two parts, and so we had the signal detection portion and the signal analysis portion. And so for signal analysis, we use a program called GRScan, which is written in C++. It detects signals by looking for their peaks within the FFT, or the fast Fourier transform of those signals. And then it determines the bandwidth, the power, the timestamp that it was located, and then it records a short recording of those signals. And then those are passed into our MATLAB script, where it matches whatever file you choose to analyze with its corresponding CSV file. And then it looks through to determine what the modulation type is. And for this project, we only looked at frequency modulation and amplitude modulation. And it was mostly a proof of concept sort of project.
Awesome. So could you tell us, like, what do you think the hardest part of your project was?
I think that the hardest part for all of us was the extremely steep learning curve that we had with not only having to learn about the GNU Radio toolkit, which is you can use both Python and C++ with it, but it comes in both Python and C++. It's for controlling your radio front end and for writing software-defined radios, and the learning curve for that alone was huge, because there wasn't all that much documentation for it, or maybe it didn't have the features that we needed or wanted. Mm-hmm. And then from there, we had to research the basics of digital signal processing, and how to determine what factors or what characteristics of certain modulation types exist, and are reliably able to be used for determination.
Okay. And being an online team, obviously, all of your members are, potentially across the world. So could you kind of talk about the experience of working with an online team and, not having the luxury of just, walking next door or driving somewhere to meet up with someone to, talk about your project or work on stuff?
Yeah, luckily we are although we're all on more or less different time zones. A few of us are in. I think we have 2 on the East Coast, although one is currently across the world right now, and then a few other out west. It's been difficult having to work on at different times on the project, but through the use of GitHub for version control, or being able to meet on Hangout meetings like this and share our screens, it's greatly facilitated us being able to work together and get the project done. There was something I wanted to say about that. No, lost my train of thought. I'm sorry.
No, that's okay. So what do you think was the one thing you probably learned the most out of this project?
I would say working with software-defined radio. I specifically worked on the signal detection portion because I had a little bit more experience with writing in C++ and working with GR scans more specifically. And so what I learned out of that was really just the basics of software-defined radio. Coming into the project, that was a topic that I was really interested in. I didn't really have all that much exposure to.
All right, awesome. And so if you had more time to work on this, an extra semester or an extra year, is there anything you would add to it to, make it better or something like that?
So one of the things, we met our target and threshold goals, and unfortunately due to time constraints, we were able to meet the stretch goal, which was using a database instead of CSV files, which would allow us to do statistical comparisons between different runs, which it would have been really helpful and a really neat feature. Another thing we wanted to do, instead of looking at statistical analysis of the frequency of these signals, we could have used something called k-means cluster correlation or whatever to determine the modulation type perhaps more efficiently and with higher accuracy.
Okay. Well, thank you for sharing your project with us and, telling it how it works and all that stuff. And good luck to you for the rest of Demo Day and your presentation.
All right. Thank you very much. Have a good one.
You too. So could you introduce yourself and then give us a a little overview of what your project was?
Yeah, so my name is Gracia Michelle Oma, and with me I have a computer vision assisted object tracking system. That is what we've been working on the past year. And so our project is a system that can track an object
So
using
could you introduce yourself and then give
like
us a
computer
little
vision.
overview of
That
what
is
your project was?
when
Yeah,
like
so
a
my
cam-
name is
the
Gracia
camera
Michelle
will be
Oma,
able to
and
detect an object
with
and
me I have
determine
a
like
computer
what the object is
Okay.
and the position of the object.
Okay.
And so it
So when you're saying it can determine what what the object is that using like kind of machine learning, or to classify what it sees?
okay, so with that we used Amazon's cloud library for the detection. So the camera looks at the object and it communicates with the from the slides you can see that. Okay, so it detects the object, then after that it goes on and to classify what the object is.
Okay. And so could you kind of describe the different components that are used in this tracking system? Because I see you have pictures on the slide.
Okay, so the different components are, we have a camera that is used for the vision component. We have a battery that powers the system. We have axle gimbals that kind of move the camera, so the camera it has the ability to move both in the Y axis,
Okay.
both up and down, and it also has another axis that can make it turn around 360 degrees, so
Okay.
that it can be able to move with the with a moving object.
Okay.
And then it also has a servo, and yeah.
Okay. And so now that you have this project finished, what do you think was the most difficult part of this project?
I think the most difficult part of the project was staying within our budget, because we definitely had to spend. So in total, we ended up spending a little bit less than $150, and that was very hard because we ended up using a very cheap camera, and that kind of messed with one of our main objectives, which was to keep the object in optical zoom. So since the camera doesn't even have the ability to do that, so that was one of the things that was kind of a bummer, because we had such a small amount of money, so we kind of had to do some trade-offs in our objectives.
So what do you think that you learned the most from this? Because obviously there's a lot of components in here, and then there's all the software stuff. So what was the one thing you thought you learned the most from during this project?
One thing I think I learned the most from doing this whole project was teamwork, because you kind of have to go back and forth, and you have different components that everyone else is dealing with, like, and so you have to find a medium for the integration of all the systems and all the different components.
Right.
So teamwork was a huge thing.
So now that so this is the poster. What do you guys have out there that you're showing for demo day? Is it the full-on camera swiveling around and tracking the? Are you guys throwing a ball or something? What are you guys presenting out there right now?
Okay, so for the demo, we had one of our team members actually walk around and record a video of the camera tracking him. And so we have a recording of how the camera is tracking his position, and you can kind of see, like, this is a screenshot of
under
of
the
movement.
results?
Yeah, under
Okay.
the results. So all the lines is kind of like where the object was moving to and from.
Okay. And that's what you guys are showing out there.
Yes.
All right. Well, awesome. Thank you for coming in and talking about your project with us, and good luck to you out there for the rest of demo day.
Yeah, thank you so much.
Yeah. problem. Could you introduce yourself and then give a brief summary of what your project was?
Yeah, so my name is Annabelle White, and my project was designing a planar ortho mode transducer for C-band satellite reception with suspended stripline. So our project came about because our partner company, ATCI, wanted to improve their Simulsat satellite receivers so that they could be used for high-definition signals, and also so that they could receive more signals per device. And they wanted to do this by redesigning a component of the Simulsat known as the ortho mode transducer, or OMT. So a Simulsat isn't like a typical satellite receiver like the one pictured here on the left. Instead, a Simulsat has a unique shape and these multiple horn feeds, which make it capable of receiving multiple satellite signals traveling at different frequencies at the same time. And each of these horn feeds is attached to an OMT. And the OMT is essentially a circuit board that can take orthogonally polarized signals that are traveling at the same frequency and separate them into two distinct transmissions. And this is a really valuable component since it effectively doubles the number of signals the Simulsat is capable of receiving, but it's also responsible for quite a significant amount of signal loss due to the board's dielectric material. So the scope of our project was therefore centered around lowering the dielectric loss of the OMT in order to make it capable of processing HD signals. And we looked at two main ways of doing this. First, by comparing the OMT signal transmission characteristics implemented in conventional and suspended stripline, basically to see if a suspended stripline circuit would perform better than the currently used stripline. Second, we explored finding a dielectric material to make the circuit board out of that was lower loss than the one that's currently being used. And we also wanted to make the OMT smaller so that more of them could fit into each Simulsat, and each Simulsat could therefore process more signals. So we found using ADS that the suspended stripline circuit was in fact an improvement over the stripline circuit, which is a very good thing. We got improved signal transmission and signal reflection reduction. So we compared about 5 different dielectrics, and we did find one that was better than the one that's currently being used, and it's called Illumina. However, Illumina is also a lot more expensive than the one that's currently being used, so it was more of a theoretical design improvement and wasn't necessarily one that would be cost effective to implement. So after we found ways to improve the signal quality of the OMT, we moved on to making the OMT smaller by attempting to reshape this rat race signal coupler. So rat races are typically ring-shaped, but we wanted more of an oval shape so that the rat race would have a smaller width and allow us to move all the attached components inward and reduce the width of the entire circuit. So our results showed that the oval rat race performance wasn't quite as good as the circular rat race performance, but the rat race and suspended stripline that was oval shaped was an improvement over the one that's currently being used. So after completing the simulation work, we designed 2 prototype boards to be fabricated, one for the suspended stripline components and one for the stripline or the conventional stripline components. And we're currently waiting to receive our prototype test results to verify our simulation work. We would have loved to have shown you all those today, but ATCI requested a few board modifications that have delayed us in getting those prototypes back. The very good news, however, is that our project was successful in finding potential design improvements to ATCI's existing OMT. The most promising combination of our results include switching from a stripline to a suspended stripline design, and keeping the same Doroid 5880 dielectric, and potentially reshaping the rat race coupler into an oval. Okay.
All right, awesome. So what do you think was the most difficult part of your guys' project?
I would probably say that was hurricane season last season, because both of my partners actually one of them lives in Dominica, and one of them lives in the Grand Bahamas. So Keith, he got hit by a really bad hurricane, right, and couldn't really communicate with us all that much for a few weeks. So that was kind of scary a little bit, but we managed to get over that and continue on.
Okay. And what did you think you learned the most from this project?
Probably microwave circuitry, because that was something that was kind of new for, I think, all of us. So it was a different experience. I actually work in control systems, and Keith and Hardley work for power companies. So, you know, we both have kind of technical jobs already, but nothing with microwave circuitry. So It was kind of nice to learn something new like that.
Yeah, they call microwave circuitry black magic. So.
Yes, I would agree with that statement.
All right, well, thank you very much for, presenting and telling us about your project, and good luck with the rest of Demo Day.
Thank you.
Thanks.
All right, so could you introduce yourself and then tell us a little bit about your project?
Yeah, my name is Mono Livingston, so I'm part of Team 24, and we're sponsored by Microchip to go work with this Adventurous Stills company, and so we can make their distillery operations automated.
Cool. So working with beer?
Yeah. So I'm working with alcohol, so it'll be more like liquor. So they brew like spirit alcohols and whiskey and stuff like that.
Cool. So could you give us a little overview of what you guys have accomplished over the past year?
All right, so we managed to actually complete this automated system, and which is actually pretty good. So this company is very happy, and they don't have to go out of business. And we actually started by just understanding how they brew alcohol first. And one of the main factors for their distillery operations, which is actually like monitoring the temperature as well as controlling the machines to turn it on and off. And so right now we actually created a system, and we actually call that system the Remote Access Monitoring Operations Distillery. So it's a pretty good system. We worked with a Raspberry Pi as well as an Arduino. So these are the two main microcontrollers that we worked with, as well as the components as relays and temperature sensors.
Okay.
And how we did it was we had an Arduino, and this Arduino reads C programming. So we had an Arduino read 3 temperature sensors. And afterward, we hooked a Bluetooth up to the Arduino to send that information over to the Raspberry Pi wirelessly. So when it sends it over, and we use the Bluetooth HC05, which is very popular and it's very fast, and also it doesn't require that much voltage. And whenever the information sends over to the Raspberry Pi processes that information, make sure that it's the correct information, make sure there's no other numbers or any kind of negative numbers. So when that processes that information, it then displays that information. And this is all written in Python, so it's a little different than the Arduino. And whenever in the Raspberry Pi, we also hooked it up to the relays too. So being that they're working with a 3-phase transformer, it drives a lot of current, so they needed something to, being that the sensors work at a much smaller current, the relay will actually help turn that on using electromagnetic signals.
Okay.
And these are the pictures on here. So I have the temperature sensor right here. I have the relay. And also we're working with an H2O valve, but we actually didn't really need it because that's the company itself working on that project. But they just sent it over and just had us work with it and just see how it works. And there's actually a ball valve. So then the ball actually turns and then it closes off and turns it back on. And how that actually works is whenever the water is coming through and the water gets at a certain temperature, that sensor will recognize that thing and then turn it off. And then whenever it gets too hot, it'll turn it back on, run cold water in it. So that's all it is.
Okay.
And then also we work with an LCD display screen that's just to view it manually. So whenever you have this still there, it'll be able to see all the temperature. And we measure temperature at the tank, the column, and the condenser. So the condenser is actually where the alcohol pours out. And the column is whenever it meets equilibrium, allows them to brew another batch. So they need to know the temperature for that. And the tank just monitors the actual, whenever the alcohol is brewing. So then it gets like really, really, really hot. So that's just wherever it starts to vaporize and then start making alcohol.
So the main thing the system tracks is the temperature. Is that like your main parameter that you're keeping track of? Okay. And it's like a very significant one when it comes to brewing?
Yes.
Okay.
Yeah, so they brew like 6 hours. So they want to make sure and know like where if there's any kind of peaks or any kind of like whenever the temperature decreases and stuff like that. And they're not actually there to see it, so they want to see it like every 5 minutes, maybe every minute, or maybe every 10 minutes, so they can have better operation. All right, so we also built a web page too because they wanted to control it or they wanted to control it over the internet. So we used this web framework, which was Django, and this Django both supports the back and front end. So the back end is just mainly for the web server itself, so it's where you have the setting, the user authentication, as well as whenever you want to make your application templates. So then the relays and the temperature, we had to make an application for that. Okay. And then also we had to make templates in order for us to view the interface of the actual web page. But that's more of the front end. So the back end is just mainly we worked with the database and we worked with MySQL in order to log out all that information down. And we used that because we didn't want to use like just an Excel file because it'll just crash the server. Okay. So then MySQL actually works well with Django. So for the front end, actually this is what the back end looks like. So this is MySQL. This is our database right here, and you can just see the temperatures logged at all different times, and you can also see the timestamp too as well. So this next one is the relay controls. So the relay controls is more like a front end part, but we also use it as a back end part too because we need to write the Python code for it to send a signal to turn on the relay to toggle the relay on and off. So I'll explain more about that whenever I get to the front end. And this is actually the front end part now. So we have our information page for our temperatures. So we have it reading the current temperature as well as the lowest and highest temperature, and also it graphs it too so they can visually see it. And this is more like a live plot, so then you'll be able to see it more like a live feed.
Okay.
This next one is the safety protocol. So the safety protocol is just for us to have alerts. So if there's a really high temperature, a really low temperature, it sends an email to the owners of it, letting them know, hey, at this time, this is what happened, and then they'll be more aware of the high and low temperatures.
Okay. So we're running a little bit over, but I think that was a very good overview of what you guys have done. So thanks for coming in and sharing that with us, and good luck out there for the rest of demo day.
Okay, thanks.
Awesome, thanks. He
Oh.
doesn't have anything.
Got it.
He has a physical object.
Yeah, should be good. All right, so introduce yourself and then talk about the project that you've been working on for the past 2 semesters.
I'm Adam Grula. I worked with Robert Wen, who's another electrical engineering student, and then Marvin Vergara and Shreya Kumar. They are biomedical engineers, so we had a joint interdisciplinary team, which was really cool. So basically what we were looking at is breast biopsy and sort of improving that process. So right now, if you get a mammogram, they see something they want to check out, they take you in, they biopsy it because half the time it's benign. You know, it's not necessarily cancerous. That's why they want a biopsy. And even if it is cancerous, it can help them sort of understand like what it is. So the current biopsy procedures, there's 2 procedures. There's a stereotactic procedure and then an ultrasound procedure. The stereotactic is more accurate, it's more reliable, but it's also not very comfortable. You lay face down on the table, they clamp the breast. It's very uncomfortable to go through. The ultrasound procedure is much nicer. It's just an ultrasound suite with them looking at it. It doesn't have the same accuracy levels though, and it doesn't have the same ability to penetrate super deep into the breast. And so we were looking to create something that could improve that process so that you could have that experience without, while still having a good accuracy and sensitivity. And so what we have here is the biopsy probe. It's bioimpedance probe. It's integrated into the needle. So we have a 1 wire running along the inside and 1 along the outside, and then we're measuring impedance across this area. So it's sort of a confirmation method. So the area of the sample being taken, you can know that that's what you're getting. So it helps prevent multiple samples needing to be taken because you can confirm it, that you have it before you take the sample. Because the normal method for confirming that you have a sample is to take the sample you got, go into a different room, x-ray it. Is it there? If not, you gotta stick a needle in again. And so by confirming it like this, we can prevent multiple needle stickings needing to go in there. We can prevent the needle needing to stay in there for too long, because I mean, this is a 12 gauge needle. We also have a 7 gauge in there that they use for these biopsies. They're pretty large. They can do some serious damage. You don't want them in there any longer than they have to be. So there's a circuit that goes in conjunction with these electrodes, and then we're measuring the signal that we're getting back and using that to find areas with calcifications.
Okay, cool. So what do you think was the most difficult part of this project?
So being an interdisciplinary team was kind of a challenge because there are certain aspects of like the biology and like needle design that as an electrical engineer I wasn't like an expert in. It wasn't really my area. And then for them, there were also certain aspects of like the circuit design and the measuring that they weren't really familiar with. And so to be able to communicate across those kind of challenges was definitely what I felt like was the biggest challenges, to make sure everyone was on the same page, even if you don't like 100% understand what's going on.
Right. Like having to explain stuff in more simpler terms to get them to understand.
Yeah.
Both ways.
Yes, definitely.
What do you think you learned the most? Was it like the biomedical side of stuff? Would you say that was the one thing you learned the most, or was there anything in electrical engineering that you learned a lot from doing this?
I definitely learned a little bit about electrical engineering. Like I'd never bought ICs before or like really implemented them in a circuit like that, like going online, making sure everything lines up. Like you have to go look for parts. But I think also a lot the biomedical end, some of because a lot more research, especially with stuff like the FDA, like what goes into getting approved for that is much bigger than like we built a robot hand or something. There's a lot more stuff that can go wrong. There's a lot more like steps to go through to make sure that everything's safe for people.
Yeah, there's a lot more liability because you're you know, putting that in people. What do you, if you had like more time, is there anything you would change about your project or anything that you would add to it, you know, knowing that you had more time to work on it?
I definitely would have. There were certain ideas. So we worked in conjunction with BD, which Bard is a subsidiary of now. So a medical company, they sort of sponsored us. They were great to work with. We actually presented basically our findings to them 2 weeks ago. They gave us a lot of really interesting concepts and ideas. And they're people who are in the field and work with it and sort of ways to apply. Because the general technology of using, you know, bioimpedance or something to differentiate calcifications is it's a really cool concept, and there's I think a lot of applications for something like that, more than just this one that we happened to choose for our project.
Okay, cool. Well, thank you for sharing your project with us and explaining it, and good luck out there for the rest of demo day.
Thank you.
So, huh? Yeah, very low key. So, could you, introduce yourself and then talk about your project that you have here?
Yeah.
I'll hold.
Okay. So my name is Samuel Perez, and this is the stroke-induced hemiparesis rehabilitation device. That's short for a rehab device that will help patients who have gone through a stroke and are facing the side effect of hemiparesis, which is a paralysis on half of the body, and that can extend from just the hand all the way to literally half of their body. So this device is the prototype that we currently have. We have 2 accelerometers, one on the index finger and then one on the thumb. And basically these are here to get feedback or get data from the environment and let us know if there has been an extension on the finger or what direction it's going in. And that will help us determine if it is a good quality exercise or if it's not up to par to what the physical therapist has set for parameters. And it's interchangeable, and it could be calibrated to each individual patient.
So this would be used during physical therapy then?
Yes.
Okay.
So this can be used during physical therapy, but one of the options that we were working on is making it able to be used at home. So as you can see here are some bands that can be easily taken off the finger and put back. And that reason is because, I'll use the hand as an example. Yeah. The initial device was actually a glove. And we went away from that idea solely because if a patient with hemiparesis doesn't have the ability to open their hand and is stuck like this, putting on the glove would be really difficult. So making these 3D printing these these holders for the accelerometers or for different devices allows us to use these sort of elastic bands, these sort of rubber bands of different sizes to be able to apply it to anybody, no matter the size of the hand.
Okay, cool. What is this hand made out of?
The plaster.
Oh, okay.
Yeah.
Cool. So what do you think was the most difficult part of this project?
Yeah. Definitely. So I worked with a team of three biomedical engineers. They focus on the functionality of the hand and different ways that we can implement. So my part was more on the hardware. And one of the most difficult parts of this project was actually getting the multiple sensors to work with a single microcontroller. There was all kinds of libraries and all kinds of examples out there, but they just were not working. And that's the reason why we put a multiplexer or MUX for it to aid the traffic from all these sensors.
Okay, cool. And what do you think you learned most from this project? Since, you're an electrical engineer, you worked with 3 biomedical. Did you learn a lot about, biomedical engineering, or was there something, with using these accelerometers that you learned a lot about? Like, what do you think was the thing you learned the most?
I think out of everything, I learned a lot about working in a team, taking in the perspective from a different sort of, different perspectives on a single project. Yeah. And I was able to, use that information to, be able to deliver the software or be able to connect the hardware together. And I guess the lesson I would learn is just teamwork. When you're working towards a single objective, it just goes hand in hand.
Cool.
Fun.
So if you had more time to work on this, say like I gave you an extra semester or something, or you wanted to use an extra semester, is there anything that you would change about this, or add on to this to make it more marketable or just better in general?
Yeah, definitely. The first thing I would do is make it wireless. Be able to connect to a phone. That way, not only are patients taking it home, but they can do it honestly wherever. And yeah, just make it more accessible. Make it compatible to smartphones so that they can see real time, which is one of the specifications is see real time the progress that is being made throughout the exercises, throughout the physical therapy session, and overall over a certain amount of time.
Cool. All right. Well, thank you very much for coming in and showing us your project, and good luck out there for the rest of demo day.
All right. Thank you.
All right. Could you introduce yourself and then talk a little bit about the project that you've been working on for the past year?
Yeah. So my name is Joseph Lee, and what we've been trying to do is simplify solar cell fabrication. This is one of our solar cells that we made. What we're trying to focus on is the diffusion process, which is where you introduce the phosphorus onto your silicon cell, basically making the PN junction. That's what makes your solar cell. Okay. So the standard way to do that would be with a large gas diffusion furnace. It costs upwards millions of dollars, right? So what we're trying to do is something called spin-on diffusion, which is exactly what it sounds like. You basically put your wafer on a spinning device, put a liquid phosphorus chemical on there that'll rotate your solar cell. That'll make a phosphorus layer on your cell. And since you already have the phosphorus on there, you don't need an advanced furnace. You could just heat it up in a regular furnace, and then that'll make your solar cell.
Cool. So what was the whole process behind, coming up with this process? Was it like a lot of research? And then what did you guys do to finalize this product?
So this one was a faculty project by Solar Powers Lab from Bill Docksher. And so he basically came up with this simplifying solar cell fabrication and studying the diffusion process. He's also the one that introduced us to the spin-on diffusion technique. That was the whole goal of this whole project, was from the start.
Okay. What do you think was the most challenging part of this project for you?
The challenging part, I would say, well, this was a lot of trial and error, basically, figuring out what diffusion processes work with this kind of spin-on. So I'd say probably time management, because the way we came up with our diffusion models at first was we used a model online, and it's pretty difficult to model diffusion. So when we would come up with the model, it would give us parameters that we wanted, then we'd try and make it, and it would not be anywhere close to what the model was. So then we'd have to go off on our own and modify the recipes again, and then we had to do that many times for each different recipe that we came up with. So I'd say probably just having to trial and error everything over and over again.
Okay. And what do you think you learned the most from this? Was it the time management, or was there anything technical in here that you didn't really know beforehand? What did you learn?
Yeah, so when we first started, we had a big overview about the standard way to make solar cells, so that was really helpful, just learning about fabrication process and everything like that. The time management was also a big part, but I think for me personally, because I sort of took on a leadership role type thing, because I was the one that put the group together, so I was kind of forced into that. I think I learned a lot about managing a team and just overall getting things organized and having people work on what they need to work on. So I'd say for me it'd probably be, I learned a lot about leadership.
Okay. And you said that this fabrication technique is cheaper than what's out there, correct? Are there any other benefits to this, or is it purely based on economic?
Yeah, so economics is probably the main thing. There's also the chemical that you would use for this is a liquid phosphorus chemical, and it's extremely safe, extremely easy to handle and ship. So pretty much anyone can get their hands on it. What the old way you would use phosphorus chloride, or POCL3 is what it's called, and that's a really toxic chemical, and you have to be, it's really hard to get, really hard to ship, and really hard to handle.
Does this way make the solar cell more efficient in any way, or is it just like you said, safer materials and then economics?
Yeah. So with this one we got about 60% efficiency compared to the standard way, which is standard way you get efficiency of about 15-16%. Right. This one's about 9-10%. But there's no reason you couldn't optimize the diffusion process. You get comparable efficiencies if we had more time.
Cool. So now that you've gone through this whole process for the whole year, if you could go back to the beginning, knowing what you know now, what's one thing you would do differently?
I guess if I would start better with the more organizational skills. I'd have a better layout of exactly what we want to do and the test we wanted to run, rather than just testing something and then coming up with the next test right off the bat based on what we learned from the last one.
Just have backup plans in place just in case.
Yeah.
All right, cool. Well, thanks for coming in and sharing your project with us, and good luck to you for the rest of Demo Day out there. So could you introduce yourself and then, talk about your project that you've been working on for the past year?
Absolutely. My name's Amin Johnson. My group mates are Mohammed Aiden and Jessica Nelson. Our mentor was Keith Holbert, and we worked on modeling proton beam therapy to determine better dosimetric quantities for proton beam therapy cancer treatment. What proton beam therapy is, just a quick overview. It's a form of radiation treatment involving a beam of subatomic positively charged particles, protons, aimed into a body, and this deposits a radiation dose. And this is more accurate than photon or gamma beam therapy because it delivers the dose in what's called a Bragg peak, which is very limited energy deposited before in front of the peak, then a high peak, and then dropping down to zero.
Okay.
And this is beneficial because you can aim this Bragg peak to deposit it at a certain location within the body with minimal irradiation to the surrounding healthy tissues. And it's beneficial for children, for tumors in sensitive locations. And there's about 28 different facilities in the United States that are operating this. And our Mayo Clinic actually approached our mentor and asked to find more accuracy and better what the accuracy of this treatment is. And so that was our goal for the semester. We did this by using M.C.N.P software, Monte Carlo and particle software, to model the different energy deposition, radiation dose deposition in the phantoms. This is a picture of our phantom right here, and the 3 different locations of the tumors that we used, the scenarios that we did for our simulations. We varied the energy, the source location, the direction of the energy, and we did all this in a modified phantom that we got from Oak Ridge National Laboratories. And this right here is just a graph of some of the results that we attained. You can see on the left, proton beam therapy, it delivers a high peak of energy at a certain location, whereas photon beam therapy on the right, it shows lots of energy in front of the tumor, lots of energy behind the tumor. All this healthy tissue is getting irradiated, which has the potential to actually cause tumors down the road, 10 years down the road. And so this is extremely important for, like I said, children, for tumors in sensitive locations, such as next to the spinal cord, such as in the lungs, or in the liver, or these sensitive tissues which are highly susceptible to radiation. So, yeah. And then this demonstrates how the energy affects the Bragg peak placement, and how different directions of the energy can affect what the energy is placed. For example, right here, this is actually 2 different graphs of the same run. This shows how it was split because the energy actually hit a bone. On the left is where it hit the bone. You can see all that energy is deposited into the bone before that. And on the right, how it missed, it's right above the bone where it missed it. And so we can see how the angle of this also is very important in making sure that the energy is deposited in the tumor most effectively, avoiding sensitive tissues like bone. Yeah.
Okay. So what do you think was the most difficult part of your project?
That would definitely be learning the code. We had to learn this very specific, very unuser-friendly code in less than a semester, and then start all of our simulations, our high-powered simulations in the second semester. We had to do all of these on our personal computers. It's a controlled software. We had to apply for it and had to each receive an individual one that we couldn't put on any of the supercomputers, that we couldn't use on anywhere except for our own personal computers. And then each simulation could last anywhere from 3 to 7 hours, depending on how many points we had to use for accuracy.
Yeah, that sounds rough. So if you ran it, and did you run it a lot at night, when you go to sleep, or was there the possibility of you run it, it hits an error, and then you wake up the next morning and nothing happened?
There were occasionally times where our mesh, our tallies were in the wrong place, or we had to do a little bit more debugging. So yeah, sometimes we would wake up and be very disappointed that we didn't get the results that we wanted. Yeah. Those 7 hours of simulation doesn't include the time to debug it, to increase simulations, to to change where it's at. So we had to learn it, and we had to debug it and modify code that we found from the 1996, 97 area, and change it to be modified to the new M.C.N.P software that's used.
All right, well, thank you for coming in and, telling us about your project, and good luck out there for the rest of Demo Day.
Thank you very much.
Right. Well, could you introduce yourself and talk about your project?
Yeah, sure. My name is Ling Liu, and our mentor is Michael Gabriel. Our team members are Jiazhou Chen, Chuan Wu, and Lin Feijiang. So before I talk about our project, I'll give you some background information. Since now we are moving into the 5G era, so the theoretically the upload speed is going to be 10 gigabytes per second, but in reality it's going to be 1.25 gigabytes per second. But that still means real-time transportation of data. So at that time, the wearable device is going to be really popular. So I'm proud to say we are kind of the pioneers in here. So we are making a wristband which monitors all the conditions of the astronauts. So you can see have the ambient temperature, the body temperature, and the heartbeat rate, and the muscle. And the most interesting part of this part is muscle sensor. So as you can see, if I relax my fist, so the number is going down. But when you clench my fist, the number is going up. The number is going up, but it does have a little bit delay, which is already good for the calculation. And as you can see from this graph, the peak value is 999 millivolts. So which means when you clench your fist really hard when the astronaut is working. So this is for there's a health condition due to a long time traveling of the astronaut. It's called muscle atrophy. So we can simply see from the graph that we can know they have the muscle condition by simply looking at the peak value is going down. And also for calculating the average peak value of the muscle sensor values, it will give us the workload of the astronaut during the last week or last month. And another very important part of this project is it has a really low power dissipation. Because as you know, the heart beating rate for the normal human beings is 60 to 90. So, but when you fall asleep, it's going to get down. So we set a system building in this program is it will automatically shut down when the average heartbeat is lowering 5 to 10 range. So which means shut down at the nighttime. So which gave us a very long battery lifetime is 48 hours. So even with the NASA limit is pretty good. So and by recharging this project, just simply plug the USB into the computer, and it had the light speed recharging. It takes 3 hours to charge all the battery, and also you can upload all the data from the project into the computer by charging the USB port.
Awesome. So you said that this is for astronauts. So when you were looking at components that go inside, were there any special things that you had ordered to withstand being up in space, or is there not really that big of a difference in terms of components?
Oh well, if we take the project to the space, this shell is not workable. because this is used for 3D printing lab in the Kennedy Library. But in the future, for the most important part is the radiation. So we were going to build a metal shell of this part to preventing the radiation in the space for the future use.
Okay. So what do you think was the most difficult part of this project?
Well, I would say there were two major problems. The first one is programming, of course. So because as electrical engineers, we always have a hard time at learning the code. So we combining the analogs, the digital codes, the digital sensor values into the motherboard, then combine all the code into the OLED monitor. So the programming takes a long time with the Arduino, and also we use Python to connect with Arduino to show the graphs by simply using the Python interface. Right. And the second one is the soldering. As you can see, the size of this one is really small. Right. So, but it's got 4 electronic parts inside. So the soldering it takes a lot of patience.
Almost like
and
surgery, right?
Exactly. Yeah.
All right. Cool. Well, thank you for coming in and showing us your project. Yep. Seems pretty cool.
Thank you.
And good luck out there for the rest of demo day.
Thank you.
So could you introduce yourself and then, briefly talk about what you guys have done for the past year?
Yeah, I'm Josh Kinney. This is our project on electric vehicles, kind of the impact it'll have on the power grid today as we go more and more electric. These are my other teammates. We have two mentors. One is Professor Liao, who's a hardware designer. He's helping us design the robot. And Wang actually has a grant with the DOE to kind of create this project and see what the effects will actually have in the future. So this is a picture of the power grid kind of that we have today. This simulates like Phoenix, Tempe, Chandler, and Scottsdale. They're all interconnected just to maintain stability and make sure that we have constant power. This is an overview of kind of the current electric vehicles that we have on the grid itself. San Jose is currently the largest electric vehicle population in California at right about 10%. Some other countries have far more than we do just because of restrictions and things like that. This is just the vehicle growth itself, kind of the way we're moving, how many more electric vehicles are coming to the grid now today. So the robot itself, you can kind of see it down here in this picture. We designed to be self-balancing, 2 wheels. This has different purposes also for the grid and testing. It's able to turn much sharper than you can see a normal standard car. This is just easy for us to test. Also in the future and in some other countries, size is a big deal, so 2 wheels will be able to reduce that effect. This is just simulating the wireless charging itself. When a vehicle pulls over to a charger, it'll begin charging automatically just to keep it charged. This is another picture of the robot itself, just an overview of what it looks like in the current one that we're using. This is the test grid itself. Basically, we'll be able to put our robot with 20 others into a smart grid test bed that will read all the voltages and currents that were being used in order to study the effect it actually does have on the grid itself. Eventually, we'll be able to make these AI, where they'll be able to decide if they want to go to a low price station that's charging or a high price, depending on how much electricity that the vehicle has left, how far they'll be able to make it, and then they'll also interact with each other inside the grid itself. Yeah. That's our project.
Right, cool. So what do you think was the most difficult part of this project?
The most difficult was probably getting the robot to self-balance. There's certain parts in the code that you can change in order to make the robot more stable. Right now, I think it's at about 10 degrees. It has of an angle before it will reconnect or recorrect itself to maintain stability. Just kind of working with that code and getting it to be more stable and so it doesn't rock as much back and forth while it's charging and also when it's simulating itself in the grid.
And what did you learn from this project? What was the one thing that you know, when you came into it, you didn't know very much about, but then you came out of the project, you're like, I know a lot about this now?
I learned a lot, I guess, about kind of the impact these vehicles are having on the grid. Before, I didn't really necessarily think about what would happen putting in electric vehicles. You know, they sound great. Everybody wants to add them to today, but the impact that it'll actually have on our sustaining grid right now, just learning more about that. And if we have the ability right now to actually support going 100% electric. Right now, because we only have about 10%, it's not a huge deal. But as we move more towards electric, it's going to have a pretty big impact on the grid itself. And if we need to make modifications, more transmission lines to tie grids better together, kind of the effects it will have ultimately on the grid.
And if you had more time, to do your project, is there anything you would add to it or anything you would change that could possibly make it better or, more marketable or something like that?
I think just being able to make this grid a little better. We have a mock-up grid currently displayed, but the ultimate grid is in another engineering building. But also being able to make the grid and all 20 robots. We only have about 3 robots right now, so they don't interact necessarily all together as like 20 robots would, and we'd be able to see more of the effect it will have on that power grid.
Okay. Awesome. Well, thank you for coming in and sharing, and good luck to you for the rest of demo day out there.
Thank you.
So could you introduce yourself and then talk about your project?
I'm Brett Fennelly. Our project is an advanced photovoltaic inverter. The project goal was to take a 90 volts DC voltage coming from a solar panel and convert that into a 60 volts, 60 hertz signal that we could use with the grid. It was also designed to have adjustable reactive power injection, which would improve efficiency and viability of using solar panels. So the approach was an H-bridge inverter shown in simulation right there, controlled by a TI EZ DSP board, which outputs 4 pulse width modulated sine wave signals, which are shown on the right. For the results, during the initial high voltage testing, the hardware failed, and after repairing the components and testing again at low voltage, we did receive the 60 hertz sine wave we expected. And then after ramping that up again, the hardware failed again at high voltage. We believe our diodes weren't rated high enough. The voltage they were experiencing was higher than what we expected them to. Here we have a video of the low voltage working. There's the setup and then the 60 hertz sine wave being shown on the oscilloscope there. And so for the advanced functions, we never got around to testing since the board was ruined at high voltages.
So what is the application of having of this project?
So if you have a large solar farm, a farm of solar panels hooked up to the grid has something called, there's reactive and active power. And we like to keep the power factor, meaning the amount of reactive power, kept low. And so we can inject or remove reactive power from the grid to keep the power factor as close to 1 as possible, which is where we're using the least amount of current to generate real power that we can use for motors and stuff.
So what do you think was the hardest or most difficult part of this project?
Learning and coding the DSP board, simply because we're all power electronics people and we don't have a whole lot of experience with that.
So would that be the thing you probably take away? You know, the one thing you learned about the most was coding?
Yeah.
Or were there any like soft skills that you learned throughout this project, kind of like time management? Could you talk about that?
Time management and teamwork. Yeah, we should have, we didn't anticipate that the basic inverter would take as long to get operating, and we kind of underestimated how long that would take. So time management played a role here too as well. It's very important.
Did you, or if you could, have more time to work on this, are there any things that you would add to it to make it better, or anything like that?
Yeah, so switching out the components that we have that we think were failing with components rated for higher voltages and currents, just so that we could get it operating at a voltage that would be practical for use with the grid. Right now, it's a 5-volt wave, which isn't useful for most electronics.
Got it. And so now that you've gone through this whole process, if you could go back at the beginning and like redo it, what are some things you would change?
Initially, just give more leeway for the components in terms of what voltage they're rated at. Also, start earlier with trying to get the EZ DSP board to work. We ran into a lot of problems with that, and that was holding back coding some of the advanced functionalities and stuff.
All right. Well, thanks for sharing your project with us, and good luck to you out there for demo day.
All right, thank you.
Yep. could you introduce yourself and then talk about your project?
Yeah. My name is Edward Ajurian. Our project is the electric motorcycle conversion kit. Basically, we take gas-powered motorcycles that have been basically put out of use or decommissioned and convert them and bring new life into them using sustainable energy and the excitement of electricity.
Okay, so could you go into more detail about how this works? You said it's a kit, so it's something that you could just buy and, or if you have a decommissioned motorcycle, just kind of hook it up yourself?
Yes. So basically what would happen is that you send in the specs of your motorcycle, and once we get those specs, we actually start building the motor mounts, the battery packs, and the controller modules to make sure that it all fits within the original specs and OE measurements of the bike itself, so that your fairings and all the cosmetics would actually fit right back onto the bike with little to zero modifications to them. And not only that, you would also get the rejuvenation of that motorcycle. So say that motorcycle sediment has a sedimental value to yourself, you can bring that bike back to life and enjoy it again in its new light.
Nice. So what are the components that are part of the kit that you guys are converting into electrical parts?
So the biggest thing is the motor. That's the hardest part of any motorcycle, because a lot of motorcycles already have spring tension built into them and they have all their parameters already set. We actually had to modify our motors to fit within the original specifications of the original manufacturer's motorcycle. Now, when we do that, we mess with spring tension and spring rates. So we had to recalculate all that kind of stuff and rebuild it up to spec to make sure that the bike kept its balance, center of gravity, and all other original specifications that came with it.
Okay. So what is the process behind building, like redoing the motor? Like where did this idea come from?
The idea came from the fact that it was actually a funny story. My mom said I couldn't have a motorcycle. So I made a bet with her saying that if I built my own, would she let me have one? She said sure, because she thinks that I can't finish projects. And lo and behold, one day she comes home and she sees this electric motorcycle parked outside and me standing by it saying, told you so. So that's where the idea came from. The idea of people can bring their own bikes and come back with it with an electric, sorry, is this live?
Yeah.
Oh, awkward. So this bike will actually rejuvenate itself, and people can learn off of these processes that you can learn building this bike and bringing it back up to spec.
Okay. So if you did send in like specs to you and you wanted, how long is like the turnaround time for you to actually get all the components together and send it back?
So because the first time around it took about 3 years for me to do all the research, and then this time around it was about 8 months. The team, if I had a viable team, I would probably be able to turn around bikes within 4 months, 4 to 6 months now, because all the research is practically done. We've upgraded from DC motors on the original bike to AC motors on the new bikes, which is what we have currently out there. And we also are working to develop better battery systems instead of using scavenged Nissan Leaf systems.
Okay.
So,
What do you think was like the hardest part of this project? So you said you've been working on it for a long time. So what was the hardest part?
The hardest part, save for obviously funding, was the fact that a lot of these bikes are much older than people anticipate. Newer bikes you won't see decommissioned nearly as often as you see older bikes. And in my past experiences, the last 2 projects I've worked on have been pre-2000s. And manufacturers don't really design bikes for that mindset that they're going to be probably converted or bigger engines are going to be put into them.
Right.
Now, the fact that they don't count for that, you have to make modifications to the original frame, including adding gussets, trusses, and any kind of structural rigidity to make sure that the bike doesn't buckle, bend, or in the uneventful case of an accident, in this case, because lithium-ion potentially harm the rider or cause fires like we've seen in Tesla vehicles. So creating a shield, creating trusses, and creating a rigid frame that actually accounts for all the original cosmetics is probably the hardest part.
Okay. Well, sounds like a really cool project. I can't wait to go out and actually see it. But thank you for explaining it to us and, presenting, and good luck to you for the rest of the demo day presentations.
Appreciate it. Thank you so much.
Could you introduce yourself and tell us about the project that you've been working on?
Yes, sir. I am Logan Siska, a senior electrical engineering student at Arizona State University, and this is our remote acoustic sensor nanolab for EEE 489. So we've actually gone ahead and designed, built, and tested a spacefaring payload that will actually launch to space later this year. So I'd like to introduce you to our project now. So this is a picture of our nanolab. To give you an idea of the size, this is about the size of a loaf of bread. Okay, so 8 inches long there. And I've gone ahead and labeled the different components of the nanolab. So just a general overview, this is a sensor that allows us to listen to phenomenon that we can't typically hear. So for example, in the vacuum of space, you can't hear anything because there's no medium to transfer the sound. So instead, with our remote acoustic sensor, we can point it at a target and observe the modulations in light that are either reflected or transmitted through that target. And if there's a phenomenon that produces sound, it will have an effect on those light waves, and we can pick up those changes with the phototransistors in our sensor array. And with just some very simple post-processing, we can take the voltage waveform and convert it into an audio file. So in that way, we can listen to things in space that we've never been able to hear before, which opens up a whole lot of opportunities. So in this picture here, you can see the remote acoustic sensor itself on the left there, the LEDs that we'll use as a light source, and there's a little clip art picture of a honeybee because that is the target of our experiment that we'll be studying throughout the flight to space. And finally, there's a flight computer that will actually collect the data and an interface to the rocket. So you may ask, how are we actually launching this to space? First, I'd like to discuss why we're actually doing this. So our primary goal is to demonstrate that this technology will work in weightlessness in the vacuum of space. And that's because we've partnered with Ecliptic Enterprises, which is a leading company in the space industry that produces cameras for rockets and spacecraft. So they want to demonstrate this technology in space so they can commercialize it for future missions. So we're pioneering this technology by creating our own sensor and flying it later this year. Secondly, this provides great opportunities to inspire the public because we're bringing sound to these phenomenon that we've never been able to listen to before. So it really makes videos from outer space much more exciting to actually hear these things that are happening. And finally, as I alluded to, we're flying honeybees inside of the experiment box in order to study their flight behavior in microgravity. So we want to learn how the bees react to being in space, because bees will be crucial to pollinating crops on Mars and other planets that humanity will colonize in the near future. So we're answering those fundamental questions. So now we're able to do this because of a competition that was sponsored by ASU New Space. And we were selected from a pool of 7 teams, us and 2 other teams, to further develop our payloads and launch them on this Blue Origin rocket in the fall of 2018. So we're very excited to be awarded this opportunity to fly our hard work to space. To give you an overview of what the launch will look like, you can see the rocket there taking off on the left. We will be in the blackness of space and weightlessness for 3 minutes there in that middle picture, and then we'll come back to Earth softly 10 minutes later. So this gives us a great exposure to zero gravity up in space so we can demonstrate this technology. Here you can see a picture of 3 of the circuit boards that we developed for this project. On the left are the LEDs that transmit the light, and on the far right side is the remote acoustic sensor that picks up those changes in light, digitizes it with an analog to digital converter, and then sends that data to the Raspberry Pi flight computer in the bottom center there. We also have a Mobius camera to look at the action and give us live video of the bees as they fly around the experiment box. And then finally, I'd like to present the results from our prototyping. So here you can see a audio waveform from 2 independent honeybees that were flapping their wings and intercepting that LED light. And we were able to pick up the changes in light and then convert that to an audio file. So I'd like to go ahead and play that for you. So if you listen closely, you'll hear 2 different bees flapping their wings and creating a buzzing sound. So if you could hear that, that was those 2 bees creating a buzzing sound, and we've proved that this sensor is able to pick up their wing beat, and we're looking forward to further refining the payload over the summer, subjecting it to a whole host of environmental tests. That way we can ensure that the payload will be safe and operate correctly when it flies to space later this year.
Awesome.
Do you have questions?
What do you think was the most difficult part of your project?
Sure. So certainly being a fully online team, we're distributed over the globe, actually. We have one student who's on a naval vessel in the Pacific Ocean right now. So it introduced us to some of the challenges and advantages of having a global team. So communicating with him out in the ocean, sometimes he had spotty internet connections. So we had to look at ways to schedule our resources and our meetings that way we could collaborate together effectively.
Okay, awesome. Well, thank you for sharing your project with us, and good luck with the launch and everything, and good luck with the rest of Demo Day.
Well, thank you very much. I appreciate it, Richard.
All right, thank you. Could you introduce yourself and tell us about your project?
Okay, so I'm Rafael Acuna. Our project is a data acquisition based board for a system that is meant to measure, not measure, but characterize the elements on the surface of planets, basically. Okay. Yeah, it's based on neutron spectrometry. So this device is meant to be on a satellite, which is with a proton source, neutron source, gonna shoot to a planet's surface, and because of that, neutrons and gamma rays are gonna bounce back. Then after that, it goes to a first stage of a scintillator, which is a device like brights up that emits light based on radiation. Mm-hmm. Then after that, light is multiplied and converted into a pulse current, and then it's also amplified, and then that's where our data acquisition board comes in to read that pulse, basically. Okay. And the thing that our board does is that it detects, detects three things on the pulses. It characterizes the height of the pulse, like the width of itself, and also the energy, which is based on the integral of said pulse. Okay. And with those three things, you are able to discriminate between neutrons and gamma rays, and with that ratio, you can determine like a lot of the element characterization on the surface of that planet.
Okay. So what is the application of characterizing the surface of a planet? Like what is the motivation behind this?
The main motivation is to find or detect hydrogen in planets, which is closely related to water, most of it. Yeah. This is a project from ASU, from the Electrical Engineering School and the School of Earth and Exploration as well. Mm. Both are like working together on this project, and it was like started like a few years back.
Okay. So, what did you think was the most difficult part of this project?
I think coming out with like specs to design for, because like we have real data of real like pulses, but that something was not able for us because like some other teams had it or it was not able for us, so it was kind of hard to design for like a bandwidth if you don't know what that set bandwidth is. Mm-hmm. So I think that was a hard part. Also, just communication like from the team, like us working with like the other teams like around, it was kind of like tricky. Okay. Just getting to know what they expected and us, just communication itself.
What do you think you learned most from this experience?
Before this, I didn't know anything about microcontrollers, like how they work, like register level. Mm-hmm. And for data transfer solution that we provided, we had to like optimize our code and our instructions based on the registers of the microcontroller we used. And we used a Arduino Duo to do data transfer. We're gonna switch to a more power efficient, or they are gonna switch to a more power efficient solution, like in future iterations. But yeah, that was pretty tricky, and also learning how to deal with non-idealities in circuit design. Mm. Yeah.
So you said that this is gonna be something used in space. So you had to research like how these components would behave in space, or how they would be affected.
That it will be for future iterations, I think. Okay. Like right now, we're designing like for. Yeah,
just kind of proof of concept.
Yeah, proving the concept, proving that everything works as expected, and then designing for like the actual application and actual like environment that this circuit is gonna be used in, basically.
Okay, and then if you had more time to work on it, what is something you would add or improve on this?
First off, I'll have a controller on board. Like right now, we just have like an Arduino Duo. Like off board, which is connected, but an Arduino is just like consumes a lot of power. So I kind of have the idea to use an ARM controller on board, and that will be a more fast solution, and will just be better. Also, like some of the components on board that we use to reset some like data, I think we can like choose better components for those, like faster ones, and I think those are things that I will like change as of now.
Okay. All right. Well, thank you for presenting and telling us about your project, and good luck with the rest of demo day.
All right. Thank you. I appreciate it.
Thanks.